well as its angle into a computer, the location of the target can be plotted. Unfortunately, radar does not necessarily distinguish between types of targets, so it is really only useful for detecting aircraft, where there is nothing else around for the wave to reflect off of. Although less detectable bombers had proven their efficiency in World War II, there was still no scientific method for decreasing an aircraft's radar cross-section. Despite the LO characteristics of U.S. spy planes, the U.S. could not build a stealthy strike aircraft. It was an academic paper from the Soviet Union that would change all this. Pyotr Ufimtsev was an obscure Soviet physicist who just happened to discover the secret of stealth. Ufimtsev published a paper which dealt with determining deflection angles of radar waves. Radar waves behave similarly to light waves. The law of reflection states that a light ray will reflect off of a surface at the same angle at which it encountered the surface. Thus, to get a return, a radar reflection requires a surface that is perpendicular to the incoming wave. A sphere provides the largest radar cross-section because it has an infinite number of tangential surfaces. Thus, the sphere always has a perpendicular side to any angle. While most energy directed at a sphere is deflected, the small amount that is always reflected back makes the sphere detectable from any angle. By contrast, a flat plane is only detectable from a 90-degree angle. At any angle other than dead on, a flat plane will deflect all radar energy away from the radar site. At one angle, the plane presents the largest radar cross-section, but at all others, the smallest. Unfortunately, flat planes are not aerodynamic. For aircraft, the best compromise between the flat plane and the sphere is a curved shape with a variable radius called a continuous curve. This shape allows aerodynamic flow without the sphere's infinite number of tangential surfaces to reflect radar. Inexplicably, the Soviet Union allowed the paper to be published and apparently didn't pursue any sort of stealth aircraft program. An American scientist used Ufimtsev's paper to develop a computer program called ECHO-1, which could calculate the radar cross-section of crude shapes. This gave engineers a tool for designing a stealth strike aircraft. Work began in secret to discover ways to manufacture aircraft based on ECHO-1 calculations. The lack of computing power in the 1960s and 70s meant that ECHO-1 couldn't calculate the radar cross-section of curved shapes. The curved designs of the SR-71 and U-2, which had reduced radar cross-sections, had been obtained largely by accident. The restrictions of those early computers meant the first stealth aircraft would have to be built out of flat planes. Flat planes present a design challenge because they are not aerodynamic, and if perpendicular to a radar site, they are extremely detectable. Designers determined that the biggest threat to strike aircraft is ground-based radar. As a result, the stealth fighter was designed specifically to deflect radar waves coming from below the aircraft. The result was the F-117, the first aircraft to carry the unofficial designation stealth. Advances in computer technology and research into stealth would eventually allow the computation of continuous curved shapes for reflecting radar, which would ultimately yield the flying wing-shaped B-2.
The shape of the B-2 is basically designed so that it minimizes the amount of radar that can be returned to the original source. And by, unlike the 117, which uses faceting to redirect the radar, it either absorbs it or in some cases it redeflects it a different direction.
Like the F-117, the B-2's shape was designed from the beginning to reduce radar. Unlike the F-117, however, the B-2 deflects radar from any angle.
The primary reason it's shaped the way it is to help deflect the radar away from the originating source. So once the radar beam hits the B-2, it's actually deflected into another area where the originating radar is not, so that it doesn't pick up the signal that it sent out. Therefore, it's stealthy.
The B-2 also makes full use of radar absorbent materials, or RAM.
RAM is basically radar absorbing material, so it does actually absorb the radar waves, keeping them from reflecting off of the aircraft.
Although the true composition of RAM is secret, it's likely it is made of lossy materials that contain free electrons which, when bombarded by radar waves, vibrate and convert the radar energy into heat. The result is that radar energy is dispersed across the skin of the B-2 rather than being reflected back to enemy radar sites.
RAM can be a number of things, to the way the aircraft is constructed and how those materials fit together and interact with each other, to a single layer of coating that we apply to the aircraft.
English and American scientists developed RAM during World War II, although they didn't quite realize its potential. Designed to deflect and absorb radar, RAM is an important element in modern stealth aircraft. But during World War II, RAM was applied to submarine periscopes and in radar testing facilities. In a few cases, the antennae on ships were coated with RAM to prevent them from being detected as targets by the ship's own radar. But RAM was never applied to aircraft. To further reduce the B-2's detectability, other elements of LO are implemented. To reduce the noise of the B-2, the engines are buried deep within the airframe, turning the body of the plane into a gigantic muffler. Next to radar, the heat signature of an aircraft is the easiest to detect.
Heat is used in a combat situation primarily to defeat an aircraft through its exhaust, and as an aircraft is flying through the air, it also generates a heat signature. A lot of modern missiles and can pick up on those heat signatures and use those to target a vehicle. Therefore, we try to defeat that as a means of detection as well.
Although the skin of an aircraft may not be hot, the boiling air produced by the engine's exhaust creates a contrail, which acts like a beacon. To correct the heat problem, the B-2 incorporates a long exhaust path, heat-absorbing tiles, and a dual air intake system. Below the main engine air intakes are smaller bypass intakes. The air from these intakes is diverted around the engine and mixed with the hot engine exhaust. Once this mixed air leaves the engines, it passes over heat-absorbing tiles. These same tiles are used on the space shuttle to protect it from the intense friction in the atmosphere on re-entry. The exhaust path is long and above the wing. It's not visible from the ground. The result is that the air behind the aircraft, as visible from the ground, is much cooler than when it comes out of the engine and produces no contrail. Although its existence is unknown, the B-2 may make use of a radical new technology known as radar absorbent structures. If radar absorbent material is a sponge for soaking up radar energy, radar absorbent structures are a vacuum. A radar absorbent structure is based around a hollow structure, most likely a honeycomb. The open sides of the honeycomb face out on the aircraft and are covered with the aerodynamic radar absorbent material. Radar waves strike the RAM, but instead of being dispersed, most of the energy is transmitted through the RAM and into the honeycomb. Inside, the radar bounces off the inside of the honeycomb, which is coated with RAM. Each deflection decreases the radar's energy somewhat. Even if the radar could get a solid reflection, the end of the structure is blocked by the outer RAM coating, trapping the radar energy inside.
It's a living, breathing aircraft. It sweats. Moisture and other things develop inside the aircraft. Anything that develops inside the structure of the aircraft comes out through the weep holes. And so there are little tiny holes in the airplane that allow moisture and other things that develop inside the wing to come out, and it maintains the structural integrity of the aircraft.
The result is that the radar energy is completely absorbed into the structure of the aircraft, and absolutely no reflection is possible. although there is no proof that radar-absorbent structures exist. If they do, the B-2 may very well be completely invisible to radar. This represents what is known about the B-2's stealth design and capabilities. What truly lies beneath the skin of the B-2 will likely remain classified for a long time to come. When air approaches a wing, it is forced in two directions, up and down. This creates a high-pressure area above the forward portion of the wing and below the wing. As the wing slopes away, a low-pressure area is formed above the remainder of the wing. This low-pressure area lifts the wing up. In addition, the high pressure below the wing pushes it up.
It's all about lift and drag. An airplane has wings, and what those are, another word for them is airfoils. As air travels over the wing, it creates a pressure differential between the top of the wing and the bottom of the wing. And what that produces is lift, as the low pressure seeks the high pressure area.
Traditionally shaped aircraft have two large wings supporting a central fuselage, stabilized at the rear with a horizontal stabilizer and a vertical stabilizer, or tail. Although advances in computer technology have allowed the fuselage to be more efficient, it still produces a great deal of drag. This drag not only decreases performance in terms of speed, it also requires large wings and engines burning lots of fuel to lift it off the ground and to keep it there. The reduction of fuselage drag, combined with an overall increase in lift, is the flying wing's primary advantage. The flying wing is also called a lifting body because the body of the plane does just that.
The advantages to the wing design, to the flying wing design over a traditional aircraft is the replacement of that fuselage with more wing. So that creates a bigger surface area of wing, which translates into more lift.
Instead of the traditional arrangement, the entire volume of the aircraft is contained within the wing. This eliminates fuselage drag and vastly increases overall lift. The difficulty with flying wings has always been stability. Jack Northrop's flying wing was notoriously dangerous, and in theory, all flying wings share the same inherent risks. A flying wing is stable in terms of pitch